All right, so we're going to be finishing up chapter 3 with a topic called stoichiometry. All right, so let's look at a chemical reaction. Okay, Na2SO4 plus BaNO3 2. All right, and that's going to give us products, which I will write down here. NaNO3 plus BaSO4. Now, the thing with this, it's a chemical reaction. The left-hand side is known as the reactants. The right-hand side is known as the products. Okay? And if I have my products and my reactants, they have to, in a chemical reaction, follow the law of conservation of mass. Which means that whatever number of, like sodiums or bariums or whatever it is, I have on the reactant side, I need the same number on the product side. This reaction is currently written in what we call the unbalanced form. Okay? So, to balance an equation, all right, the easiest way, first of all, a reason I want you to understand your polyatomics. Instead of trying to balance out oxygens by themselves and nitrogens by themselves and all of that, if you recognize you have a polyatomic, you could balance the whole entire polyatomic. All right? Now, I look here, I see I have 2 sodiums. I only have 1 sodium on this side of the reaction. So I need to balance that so that there's 2 on each side to follow that law of conservation of mass. I can't put a 2 there. If I do that, I change the chemical formula, and we don't want to do that. So what we use, just like we use in math, is a coefficient. We put a number out front. That number gets distributed between each ion, so there's 2 sodiums and 2 nitrates. I've got 1 sulfate, we're good there, 1 barium, 1 barium, 2 nitrates, and now 2 nitrates, and we are considered balanced. Okay, let's try another one. C3H8 plus O2 yields CO2 plus H2O. Now, what you might also see are little subscripts. G meaning gas, L meaning liquid, S meaning solid, and AQ meaning aqueous, which means it's dissolved in water, and we'll talk about that in Chapter 4 on Wednesday. Now, when you're balancing an equation like this, pick something that's in one thing on the left and one thing on the right. Balance standalones like O2 last. Okay. So, let's get to it. I'm going to pick carbon first because it's in one thing and one thing. I got 3 carbon over here. I've got 1 over here, so I need a 3. All right, I'm going to go hydrogen next because oxygen's by itself. All right, we'll balance it last. 8 hydrogen, 2 hydrogen. I need a 4 there. 4 times 2 is 8. Okay. Now, let's look at oxygen. 2 here. 3 times 2 is 6. 4 times 1 is 4. So I have 3 times 2, 6, plus 4, 10. I got 2 here. I need a 5 there. And we are now balanced. Let's look at another one. This is known as propane. This is butane, C4H10, gas. This is known as a combustion reaction, burning in air, burning in oxygen. And a combustion reaction will always give us, of a carbon base, will always give us CO2 and water. Okay, so here's our gases. All right, let's pick something that's in one thing. So we'll start with the carbon again. Let's do that. We'll start with carbon again. And we'll look at it and we'll say, all right, I've got 4 carbons. I got 1. I need a 4 here. I got 10 hydrogens. I got 2 over here. I need a 5. And here's where it gets a little tricky. Okay. Here's where it gets a little tricky. And it's really not. This one worked out where I had 6 and 4, 10. I had an even number and 2. This one's going to work out. 4 times 2 is 8 plus 5 times 1. That's 13. It's not an even number. So what do? Well, you can't use fractions and keep them there. You can't use decimals and keep them there. So if it's an odd number, what I always tell everybody is do this. Make it 13 halves. Okay, put the odd number, 4 times 2 plus 5. All right, so 5 times the 1 is 5, 4 times 2 is 8, 8 and 5 is 13. Put the odd number over 2. Then get rid of the fraction. How do we get rid of it? Now, just like in algebra, if I multiply one part of an equation by a value, I got to multiply everything by the value. So we're going to multiply this whole equation by 2. We're going to end up with 2C4H10 gas plus 13O2, and the reason we picked 2 is so that these 2's cancel out. 13O2 gases, 8 CO2 gases, plus 10 H2O gas. And we are now balanced. To be properly balanced, I need to be in my lowest ratio possible. So if I had this as 4, 26, 16, 20, 2 goes into that. Every number can be divided by 2. So I have to be in my lowest ratio possible. Now I'm going to give you homework about balancing. Plus, there's 50 homework sheet, a 50 problem homework sheet on Blackboard. The ones on Blackboard are a little bit more challenging, but if you can do those, there's nothing I could throw at you on the exam that's going to be any more challenging than that. So, what's the purpose of balancing the equation? Well, I'm going to show you what the purpose of balancing the equation is. Not only to follow the law of conservation of mass, but let's go back to another one and let's do C2 H6 gas plus O2 gas. And that's going to give us, again, since it's a combustion reaction, CO2 gas and water vapor. Okay. Now we want to balance it. So we're going to start with carbon. I need a 2 here. That works. Hydrogen, 6 of them. I need a 3 here. Okay. So 2 times 2 is 4. 3 times 1 is 3. And that's going to make it 7. 7 halves. Okay. But then we're going to double everything, just like we did in the last example. So this is actually going to become a 2. This will become a 7. This will become a 4. And this will become a 6. And then we can double check everything. Okay, so we got 2 times 2 for the carbons, that's 4. 4 times 1 is 4. Let me make that a better 4 right here. There we go. 2 times 6 is 12 hydrogen. 6 times 2 is 12. We're good there. I got 14 oxygen. 7 times 2. I got 4 times 2 is 8. And 6 times 1. And 8 and 6 is 14. So we're balanced. 2, 7, 4, 6. Okay. The reason we use this is, I'm going to draw our map again to remind us what's going on here. I don't want to draw it that low. I want to draw it up a little bit higher. Let's go right here. Perfect. So, again, it's what I know. In grams. It's the molar mass of known with the grams on the bottom and 1 mole on top. It's the mole ratio is next. moles of known on the bottom with what I want on top, and then the molar mass of what I want one mole on the bottom and the grams on top. Well, we did these when we looked at, if we were looking at C2H6, we would say, okay, for every one C2H6, the mole ratio is 2 carbons and 6 hydrogens for every one C2H6, which is known as ethane. These numbers, these coefficients out front, is our mole ratio. If we were to read these in the terms of stoichiometry, and stoichiometry's definition is the study of the mole relationships of products and reactants in a chemical reaction. If I were to read this in stoichiometric terms, what this would say is, for every 2 moles of C2H6 that reacts with 7 moles of O2, I should get out 4 moles of CO2 and 6 moles of H2O. What this means is that these are my mole ratios. And you'll usually see the answer if they don't write out the full equation, since it's a ratio. And let's say they gave you this one blank and said balance it, and you looked up the answer in the back of the book, they would give it to you as a ratio like so. 2 to 7 to 4 to 6. So we would do a problem just like we did yesterday, or in our previous lecture. We would do a problem very similar. What if I said to you, okay, we are going to start with, 35 grams of C2H6. And I want to know how many grams of CO2 did we get out? Well, that's weird. We're comparing a totally different compound to a totally different compound. Well, let's just follow our path. What do I know? I know I have 35 grams of C2H6. And if you learned anything from the previous lecture, well, if I want grams of something else, I know I can't compare grams to grams, so I must have to, convert it to moles. So 1 mole of C2H6, and we figure out the grams based on the periodic table. 1 times 6 for hydrogen is 6. 2 times 12 is 24. 24 and 6 is 30. Okay, so again, I got that from looking at the periodic table. Carbon is 12, and I got 2 of them. That's 24. Hydrogen is 1, and I have 6 of them. That's 6. 24 and 6 is 30. So our grams would cancel out. Now, our mole ratio. Again, if this was saying how much carbon is there, we would say, okay, for every one of these, there's 2 carbons and so on. But now, since we're doing different molecules, we use these up here. So it's very important on an exam or in a homework problem, if they give you an equation, the first thing you should do is make sure it's balanced. So what is our ratio? Our ratio of C2H6, which is ethane, to carbon dioxide is 2 to 4. 2 to 4. Okay. So, let's plug it in. For every 2 moles of C2H6, we should get out 4 moles of CO2. Moles and moles cancel out. And since I want grams of CO2, I need the molar mass of CO2. Now 1 mole goes on the bottom here so that the moles cancel out, but the mass of CO2. Oxygen is 16 times 2, that's 32. Carbon's 12, 32 and 12 is 44. 44 grams of CO2. Those will cancel out. Okay, and we'll do the math. Let me get my calculator out here. So I'm going to take there it is, 35 divided by 30 times 4 divided by 2 times 44. 102.6. So we need it to 2 sig figs. So well, let's make it 3 sig figs just so we can make it 102. All right. Instead of doing scientific notation, all that, we'll do 35.0. 35.0, and we can do 3 sig figs because I made it up. 103, roughly. 103 grams of CO2 is what I should get out if I react 35 grams of C2H6. Well, what about the O2? Well, let's just say it's excess O2, okay, for right now. So if I were to react 35 grams, okay, of C2H6 with excess O2, I should get out 103 grams of CO2. We call this value of the product we should get out based on our reactant the theoretical yield. The theoretical yield. Okay? So, what if I wanted to know about water? What would change? Now, I know I could erase this and do all that, but if I want to know how much water vapor I'm going to get out, I could, like I said, rewrite this whole thing. But I just want to show you that, again, if you do it once, you could do it 1,000 times. What if I wanted to know the grams of water from this value? What if that's what the question was? Well, this wouldn't change. This wouldn't change. This wouldn't change. This wouldn't change. But this would. This would now become 6 moles of H2O. This would become 1 mole of H2O. This would become 18 grams of H2O. And our value would be, all right, let's see here, 35 divided by 30 times 6 divided by 2 times 18. I got 63. So 63.0 grams of water would be our theoretical yield for water. Now, what we do with our theoretical yield is we can compare it to what we got in lab. And we do something known as percent yield and percent error. Okay? So I'm going to erase this so I have a little bit more boardroom. What was it? 103 and 63, right? So let's imagine we did this experiment in lab, and we want to see how well we did. And let's say when we did this in lab, okay, so our lab result, also known as our actual yield, or also known as, you may see it written as actual or experimental yield. Okay. Let's say we did this in lab, and when we did, we got 60 grams of H2O. Okay. In order to see how well we did, percent yield is equal to our experimental or actual value divided by our theoretical value times 100. So if we were doing for water, we would do 60 over 63 times 100. Okay. So 60 divided by 63, and I'm getting 95% roughly. All right. To do our percent error, figure out how much error we have, there is a formula. Okay. And here's the formula. Theoretical divided by experimental, or minus experimental, I should say, divided by theoretical times 100. I want to point out it's an absolute value, so your percent error can't be a negative number. So if we were to plug this in with our numbers here, it would be theoretical 63 minus 60 divided by 63, and that's going to come out to be roughly 5%. Now, I can't do math like that fast in my head. How did I know it's 5%? A little down and dirty trick is, if you're comparing percent yield to percent error, 100 minus your percent yield, the absolute value, is your percent error. But if you plug it into your calculator, 63 minus 60 divided by 63, okay, so 3 divided by 63, you're going to get 0.476%, which is roughly our 5% because of our rounding. And that's known as our theoretical yield, using it to find our percent yield and our percent error. Okay. Now let's use this same equation up here to do another problem. All right. Let's say that, okay, instead of, it's saying excess O2. All right. It says we take 35 grams of C2H6, and I'm looking for my black one. There we are. And we add it with, let's say, I don't know, 28 grams of O2. And I want to know how much CO2 I get out. Well, this time it's not excess. This time they gave me two amounts. And what I have to decide is which is going to run out first. Now, your book uses ice cream. I usually use pizza. And I can't draw. Okay, so this is why I'm in science and not art. But let's imagine to make a pizza, we need a crust, we need a can of sauce, and we need cheese. Okay, and that's going to be our cheese. Okay, we need 2 pieces of cheese, a can of sauce, and a pizza crust. Now let's say we have 3 of these. Okay, we have 4 cans of sauce, and we only have 2 pieces of cheese. Okay, we only have 2 pieces of cheese. They were overlapping, it was bothering me. All right. Well, how many pizzas can I make? Well, if I look at the crust, I can make 3. If I look at the sauce, I can make 4. If I look at the cheese, I can only make 1 because I need 2 pieces to make, all right, the pizza. So if I were to predict how many pizzas based on crust, I'd get the wrong prediction. Same thing with sauce. Well, we don't want to get the wrong prediction. We need to find which one is going to run out first, just like we're able to look at and say which cheese is going to run, or which condiment or ingredient is the word I'm looking for, is going to run out first. Okay. We call that one that's going to run out first the limiting reagent because it's going to limit how much product we get out. I can't look at the grams and say, well, that's the lower grams. That one's going to run out first because, go back to the last lecture, you can't compare grams to grams. So here's what you have to do. You have to go to this point on the map, convert it to a product. Whichever one gives you the least moles is your limiting reactant. And that one is used to find everything else in the reaction. So what we're going to do is set up 2 maps. One is going to be 35.0 grams of C2H6. We're going to come over here and we're going to say, okay, we have 35 grams of C2H6. We got to convert it to moles. 30 grams of C2H6 is 1 mole of C2H6. Okay. Ratio, 2 to 4. 2 moles of C2H6 is 4 moles of CO2. And we're going to stop there, and we'll do the math. But let's set up the other one. 28 grams of O2, 32 grams of O2 is 1 mole of O2. Ratio, 4 to 7. 7 moles of O2 should give me out 4 moles of CO2. And now we do the math. Okay. We do 35 divided by 30 times 4 divided by 2. And over here I get 2.3 moles of CO2. Down below, 28 divided by 32. You should already be able to see what the answer is going to be. 4 divided by 7. This is 0.5 moles of CO2. So, my oxygen is my limiting reagent. Okay, my oxygen is what's going to run out first. So, if I want to find out how much CO2 grams, I would use this. What I would do is put an X through that so you don't use it. Because that's going to give me the wrong prediction. That's like looking at the crust and saying I'm going to get 3 pizzas out when I know I don't have enough of the other ingredient. So I'm going to look at this one. This one's going to dictate how much CO2. It's from oxygen that I'm going to dictate how much water I'm going to get out. It's from oxygen. I could figure out how much C2H6 is left. So let's talk about that. I'm going to erase this top one because we don't need that anymore. And let's find out all the information we need to find out. So I want to know how many grams of CO2 I'm going to get out. Okay, well now I take my limiting reagent value, 0.50 moles of CO2. 1 mole of CO2, we're on the last part of the map, is 44 grams of CO2, which is 22 grams of CO2. Now I want to find out water. You start with this and go through the process and find out how much water. Except now your ratio is going to be 7 oxygens to 6 waters and so on. Okay, I'll leave that one for you to do. But there is one more I want to show there. So water is our limiting or oxygen is our limiting reagent. I believe I said we're starting with 28 grams of oxygen. What if the question asked then, how much excess reagent is left over? So if I take my limiting reagent and I convert it to products, I'm finding a theoretical yield. Okay, so limiting reagent to products, this is known as a theoretical yield, how much I'm going to get out. If I take my limiting reagent and convert it to the other reactant, I'm figuring out how much was used. So, okay, let's do it. I had 28, if I believe, and if I didn't, the math is still, the process is still the same, but I believe I had 28 grams of O2 as my limiting reagent. I believe we also had, 35 grams of C2H6 to start. Okay, so I'm going to take my 28 grams, and I'm going to convert it, since this is my limiting reagent, I'm going to convert it to grams of C2H6 to see how much was used. All right, so 32 grams of O2 is 1 mole of O2. Again, that's 16 plus 2, or 16 times 2, I should say. All right, 1 mole of O2. For every 7 moles of O2, it reacts with 2 moles of C2H6. Okay. And for every 1 mole of C2H6, we're on the last one now, I need the molar mass, there is 30 grams of C2H6. So we do this math. Moles cancel out, moles cancel out. We're left with grams of C2H6, okay? Now, 28 divided by 32 divided by 7 times 2 times 30. I'm getting 7.5. Okay, I'm getting 7.5 grams of C2H6 was used. And if they want to know how much is left over in excess, we take the 35 minus the 7.5. Okay, and remember this was 35.0 just for sig fig purposes. And what do we get? Okay. Wow, my brain just froze there. 8 would be 27, so 27.5 grams left over or excess. Okay, so what you do is you take your limiting reagent. If I convert it to a product, I'm finding the theoretical yield. If I convert it to the other reactant, I'm figuring out how much was used. And to figure out how much was left over, excess, take the 35, what you started with, minus what you used, and this tells you how much is left over. Now, why would I want to find how much is left over? Well, I'd want to find how much is left over if I wanted to make my most amount of CO2 and H2O, or give my most yielded product. Or what if this is a toxic substance and I got to figure out how to get rid of it, and I want to know how much should be left in the beaker. Whatever it is, it's usually you figure out your excess to figure out how much more O2 will I need to dump in to use that up so I can make my max amount of product given this. Okay. Now that's stoichiometry. We're going to add a little bit to it in chapter 4, but that pretty much, and it's nothing new from what we did in the other lecture, it's just where are we getting the mole ratio from? That's really, it's the same process with some terms. So homework that deals with this, in addition to the stuff on Blackboard, okay, I'm looking at page 138. Okay. 3.58 to 3.63. How about 3.67 to 3.76? Yeah, let's do 3.67 to 3.74. 3.67, so this is 138, 139. 67 to 3.74. Okay, so try those, and then we'll start chapter 4, which is up on Blackboard tomorrow, which is Wednesday. All right, guys, thanks a lot. If you have any problems with this, just shoot me an email.